It's an open source book. Oh yeah, yeah. It's so there's a link for it on the syllabus for the book. That's going to annoy me throughout the entire semester. Now we've got this damn flickery projector. But the book is it's an open source one. So I know for financial aid, if you want or if you prefer like a hard copy book, um, just send me the ICSN for it, and I'll send you a syllabus that has that as the required textbook for the book for the class, because usually they need it to be required. Actually, I don't know because this class is listed as a low resource. I can recommend other textbooks if you want any, but there's an online textbook that we're using.
Okay.
The lecture notes should be more than enough usually for everything that we'll learn in the class.
Okay.
Mm. Let's just go up any higher. Okay. All right, any other questions? All right, so let's get right into it then. So we're going to be going today over an introductory to chemistry, and then in the lab section, we're going to continue. We're going to do a safety video, a little safety debrief, and then we're going to continue lecture and lab just because we only have one day this week. So first thing we're going to be talking about is what is chemistry, right? And so chemistry is a science that deals with anything that has to relate to matter in the universe, right? And we think of matter, we think, maybe if you've heard some popular terms in physics and stuff, there's subatomic particles, there's electrons, protons, all these things that make up all the atoms that exist in the universe. And we aim to understand the properties of matter and then the changes that they undergo. Chemistry is largely the science of dealing with how the electrons in atoms interact with other atoms, right? So this is mostly materials interact through, and then I'll put a little E with a negative sign. That just means through electrons, right? So electrons repel each other. That's why, when I put my hands together, they don't go through each other, because the electrons in the atoms in my hand repel each other. And so generally, materials can be classified into three common states of matter. So we have things like gas. This would be like Earth's atmosphere, right? So this is what is a gas? We'll talk a little bit about when we're talking about classifying different states of matter. Gas is going to be anything where the atoms in the substance tend to be far apart from each other, right? So the atoms tend to be far apart. You can imagine in the air around us, the atoms are a lot farther apart than the atoms in the table in front of you. Then we have liquids. So liquid would be like water on Earth. And then we have solids. Solids can be anything that has atoms, and the way we classify solids is, we talk about their shape and their volume. Solids are going to have atoms very, very close to each other. And so this can also be water. Under what conditions can water be solid? Ice, right? So water that is frozen, right? And really the difference between the liquid and the solid in this case is that in the solid, the atoms are not allowed to move around each other, whereas in liquid, they actually can move around each other. So the atoms and molecules can move around each other, even though they're both close together, right? So both liquids and solids they're roughly around the same distance from each other, but one allows for movement and the other one does not allow for movement. So these are the kind of three common states of matter that you'll see in chemistry. As we've explored and learned more, we had other classifications for other states of matter, right? So there's more complicated states of matter beyond just gas, liquid, and solid. And maybe, has anyone heard of any other states of matter that aren't gas, liquid, or solid? Aiden? Yeah, plasma, right? So plasma is one. So these are the simple states of matter. And simple is a relative term. And then there's complicated states. And when I say a state of matter, that just means like, how do we classify it, based off the distance between the atoms? So we can have something like a plasma. Does anyone know where we might see a plasma? Yep, the sun, right? So the surface of the sun is a plasma. Surface of the sun, or if you light a fire, right? So that light usually comes from electrons that are moving around, they emit light, and that's a plasma. A plasma is usually just electrons that are floating around in space. And then something else that we might not think of could be like a glass, which is another odd state of matter, right? So glass and diamond, to extend, this is a state of matter that looks like a solid, right? So like your cup, you wouldn't ever think that that's not a, solid, right? Because in the time scale of the existence of the Earth, it stays as a solid, but over time that'll actually move and deform like a liquid does. It's just, it takes a very, very long time. So those are called glassy states. So those are some of the complicated states. We're not going to be focused on them at all in class, but you probably, or you may have seen those, maybe watching like Neil deGrasse Tyson or something on Netflix if you haven't taken a physics course. All right, so the chemistry, again, is the study of matter and the changes between that it undergoes, right? And so these changes, right, we can think of water as an example. Water can go from liquid to solid, right? Chemistry is a study of how does liquid water go from liquid to a solid? What causes that change, and how can we describe it accurately? Does anyone have any other idea of changes matter can undergo? Maybe something a little bit more like common to what you think of when you think of chemistry. Cooking, right? So when we're cooking stuff, matter is changing, right? So like when you cook an egg, it starts off as like runny, translucent, and you put it on the pan and it turns white and it starts to solidify, right? That's undergoing a change in matter, and what's happening is you're doing a combustion reaction on the material that you're cooking, right? And so that's another change in matter that we can have. Change in matter, so different change that they can undergo. This can be like changing from liquid to solid, or a chemical reaction, right? And so when you're cooking something, usually you're making a chemical reaction happen, right? And that's usually what we think of when we think of chemistry, right? Like we're synthesizing different molecules, maybe different medicinal drugs, things of that nature, right? We're making molecules. So chemistry encompasses all of that, right? And so it's a huge field of study, which is why intro chemistry can kind of be confusing at times, because this can touch into biology, to physics, to materials science, to different types of engineering, right? There's a huge, broad umbrella that chemistry encompasses. Okay, anyway, we're good to go on? All right, so chemistry is a natural science, right? And so I know you guys have probably seen this many, many times throughout your life, so we'll just talk about it for a little bit, right? So the scientific method is the method that we use to understand chemistry. People also use a scientific method to understand fields that are not necessarily a natural science. So something like understanding human behavior, wouldn't be considered one of the natural sciences, but people can use this method to study human behavior as well. And so it's really a process of creative thinking. And so I think a lot of people, when they think of, being creative, they think of painting, making music, being a sculptor or something like that. But scientists tend to also be very creative in the way that they think as well, right? So I always say, everyone's brains work differently. The same way that one person might see words flow onto a piece of paper when they're writing a nice essay is the way that someone like Albert Einstein saw equations and how they related to the universe around him, right? So it takes a lot of creativity to come up with these ideas. And if you've ever tried to design something or anything of that nature, you know that it isn't necessarily an easy process, right? So it takes a bit of creativity. But the scientific method also incorporates something that allows it to stay self-consistent and to stay objective in its observations, right? So it's something that's generally always changing, right? We're always building on knowledge. That's why Einstein said, well, I stand on the shoulder of giants, because he's continuing work that was started hundreds of years before him, right? And if it wasn't for those discoveries, he wouldn't have come to the realizations that he did in his lifetime. And so there's a way of like doing this and making sure things are verifiable, right? And it's generally composed of 4 steps, right? Does anyone remember what those 4 steps are? Hypothesis is going to be in there, right? So we have hypothesis. Hypothesis, observation,
Experiment.
experiment, and then conclusion. Right? And generally they go in order like this, right? We make an observation about the world or the universe around us. We come up with an hypothesis as to what explains that observation or phenomenon. And then we perform an experiment to test the hypothesis that we made. And then based off of that, we can generally come to a conclusion. And so it's really like an iterative process. So you guys can think of this as like an algorithm, as maybe a software engineer would describe it. We use an observation to observe a natural law. Then we make hypothesis and an experiment, right? And oftentimes this right here is what we would say is an iterative process. That means it's something that we have to do over and over again, right? We kind of have to fine tune our question and experiment to really get to a meaningful conclusion, right? And so this is what this is the kind of the meat of the scientific method, is that you have to come up with an appropriately phrased question, right? If you ask something that doesn't make any sense, an experiment can't really test for the existence of something like that. So sometimes you ask the question, and then your experiment shows something that's completely, you ask kind of a question with your hypothesis, and you make a prediction about what's going to happen, and then your experiment shows something completely different, right? So now you have to rephrase your hypothesis, and then redesign your experiment to test for that new hypothesis, to potentially explain that new phenomenon. And so this is why, I like to use the example of physics just because it's kind of easy. With Newton's laws of physics, they hold true, right, in certain limits of modern physics, right? So has anyone heard of quantum mechanics? Right, so Ant-Man and stuff is popular these days, and he goes to the quantum realm. And what quantum mechanics is it's related to chemistry because atoms are inherently quantum mechanical, but it's the physics of things when they get very, very small. But when Isaac Newton was working, they didn't even know atoms existed, right? So all of his theories about force, mass, acceleration, and stuff, those were all independent of an understanding of how the super small world acted. And so Isaac Newton's laws aren't invalid, but they were expanded once we discovered quantum mechanics, right? So the kind of questions that he's asking can be expanded in a new hypothesis. And in the limits of quantum mechanics, as things start to get large, they recreate Newton's laws, right? So that's why when people sometimes talk about a theory, they say, oh, well, it's just a theory. But generally, a theory is something that's been tested over and over and over again. And it isn't something that is just disproven by the existence of new information, right? So theories are theories because they can constantly be modified, but they are not theory in the sense that they're not verifiable facts for the most part. Okay, so like I said, you guys have probably seen the scientific method many times in your life. So if you're given each of these statements right here, let's think about how we would identify each of these, right? So if we have drinking a coffee at night keeps me awake, right? So I know that it does that for me these days. So how would you classify that in terms of scientific method? Is it observation, hypothesis, experiment, conclusion? That would be an observation, right? This is something that you notice that's happening in the world around you. So this would be an observation of the world around you. What about I will try drinking coffee only in the morning? That's going to be the experiment, right? That's a specific test that if we did have a hypothesis that we are trying to, see if that's what's keeping you awake at night. So this would be our experiment. And then the last one, if I stop drinking coffee in the afternoon, I will be able to sleep at night. That would be your hypothesis, right? So this is before you perform the experiment. You're thinking about, okay, if I stop drinking it, then I predict that I will be able to sleep at night. Why do they even have these in here anymore? I will be able to sleep tonight, right? So that'll be our experiment. So you can see why it's good to come to lecture, right? Because if your YouTube and your volume was way too loud or something like that. Oh yeah, that was the hypothesis, yeah. Thank you. right? So I don't want to spend a large amount of time on the scientific method, just a quick review as to why, this is considered a science and what kind of sets science apart from other disciplines, right? So, but I know you guys have seen this a lot, right? So that's just to remind ourselves of that. All right, so next thing we're going to be getting into some key math concepts, some mathematics that we should be familiar with when doing well in this course, or just some stuff that's going to pop up a lot. We'll do a review as they come up as well, but I kind of want to take a little bit of the first day just to kind of go over some of this. So one of the things you should be familiar with is calculating percentages, right? So we'll talk about that, This has to do with parts of a whole, right? And so when we talk about concentrations of solutions and stuff, a lot of times you think of something that we call molarity, which is the amount of moles of something in a specific volume. But we can also, if you work in medicine or medicinal sciences, a lot of times they will use, volume by volume percent concentrations, mass by volume percent concentrations. So calculating percentages is important. Solving equations, so this means solving algebraic equations, and I put EQN, that's just abbreviation for equation, right? So solving algebraic equations, can we isolate a specific variable if we're given an equation? So if we had something like PV equals nRT, could we isolate P, which stands for pressure in this case? And then unit conversions, which I would say is probably the most important thing that you'll be able to do in chemistry. And if you understand unit conversions, I say that probably gets you, 90% of the way there of doing well in chemistry. And so this includes things like going from one set of units to another. Does anyone know what I mean when I say a unit here? Or give me an example. Yeah, exactly right. Like kilograms, so that'd be a unit of mass, right? Or meters for a unit of length, right? So units going from one to another, right? Can we convert between them? This also has to do with something that we call dimensional analysis. And dimensional analysis is kind of another thing that a dimension is interchangeable with a unit, right? What are the dimensions of R in that equation, for example? That's just saying, what are the units of R in that equation? And so a lot of the times, the way you can check your work, or let's say I'm a little lost in this equation, I don't know if this is coming out to the right answer, you can always check your units. Are your units working out? Do they make physical sense, right? Let's say you're trying to solve for the mass of something and you end up with an answer that has temperature. Well, it's like, okay, well, that can't be right? So the units are a way that we can check our work as well. And that all falls under the term dimensional analysis. This helps check work. And you'd be surprised how many famous equations and stuff were kind of birthed from just dimensional analysis, meaning, well, I know I want my final answer to have something units that look like this, so I think if I know these things have these units and I combine them in that way, that I will get to the units I want. And a lot of times that's how some important discoveries can be made. All right, so these are the math concepts that we're going to be reviewing today and that we'll be going over and using throughout the course, right? All right, so if you're calculating percentages, to determine the percentage, we divide the parts by the whole, and then usually multiply it by what? Right, in the last step. So if we have, 3 marbles in 2 blue and 1 red, and we want to find the percent of the blue marbles. Right. We take the number of blue marbles divided by the total number of marbles. That's what we mean when we say the parts divided by the whole, right? So this is going to equal the number of blue marbles divided by the total number of marbles. And we know that at most, the blue will equal the total, right? So this is going to be a number between 0 and 1, right? If the blue is less than the total, then it's going to be less than 1, right? And so to get a percentage is a number usually between 0 and 100. What do we multiply by? 100, right? So we just multiply by 100. And then that will give us the percentage when we do this. So this would be 2 divided by 3, so that'd be about 66% is what we would get in that case. So here we have an example. We have a aspirin tablet, has a mass of 545 milligrams, right? mg stands for milligrams. That would be the dimension or the unit of this quantity. 325 milligrams of active ingredient, right? So this is what people say when they say, well, you know, a lot of times, especially if you're taking like a protein supplement or something like that, there's a lot of other junk in there, right? Just because you have 545 milligrams of it doesn't mean that it's all going to be whatever amino acid you're trying to take, right? So only 325 of that are the active ingredient. The percentage of the active ingredient can be calculated how? So why don't you guys take a second and calculate what the percentage of the aspirin would be in this case. The percentage is always calculated by dividing the parts divided by the whole times 100%. And in this case, what would the parts be? What would be the parts? It would be 325, right? This is the fraction that we're interested in for the aspirin, right? So this is going to be 325 milligrams divided by the whole, which is 545 milligrams, right? Because that's the total mass of the tablet. 545 milligrams. And we multiply that by 100 to get our percentage. And what happens to the units here when they're like this? They cancel out, right? So the same way when we divide a number by another number, units can cancel out when they're in equations like this. And here, this will make a little bit of sense to us that the units cancel out because a percentage is always a dimensionless number. It's always a unitless number, right? Because it doesn't have any physical meaning. It has meaning in the sense like how much of this unit is part of the whole unit, right? So this should always be a dimensionless quantity. And so when you guys plug this in, what number did you guys get? 59? Did I hear that? 59.16? 0.6, okay. Usually I have a hard time getting people to volunteer answers, but that was like overwhelming, so that I couldn't isolate the answer. All right, so 59.6% of the tablet is the active ingredient. All right, and again, this would be a unitless number. Okay, any questions on that? No questions? Okay. All right, so here's another, went the other way. How did I go that far back? Another one, so we have a bag. Gumdrops contains 16 orange gumdrops, 8 yellow gumdrops, and 16 black gumdrops. So this might seem like a sillier example, but this is probably more similar to what you'd actually do in the lab, right? So we have a bunch of different data points, and then you need to calculate the percentage from the data points that you have. And the data points here are just how much of each type of gumdrop do we have. And so what is the percentage? And we won't do each color. We'll just do, you know, what is the percentage of yellow? All right, so what is the percentage of yellow gumdrops in the bag? The parts divided by the whole. And the parts in this case would be what? What is the part that we're interested in? 8 yellow gumdrops, right? So it's 8 gumdrops. So our unit here is gumdrops. And the whole in this case is what? 40, right? And how did you get 40? Yeah, the whole is going to be equal to 16. I'm going to put GD for gumdrops plus 8 gumdrops plus 16 gumdrops. And we multiply all of that by 100% to get the percentage, right? And so the whole in this case, whole is just another way of saying the sum. The sum is when we add them together. So in the previous problem, we didn't have to add anything together because it gave us the total, the whole amount of the pill. But if it just gave you the components, then you have to add the total amount. And so this is important when we have data sets measuring different things and we want to find the percentage that gives a certain response or something. So we'll see more of that in the lab. And so if you do that, you should get something like 1/5 times 100%, which will give you 20%. Is that the answer everyone got? Okay. All right, so percentages, thumbs up, side, down. Okay. All right, so the next thing we talked about was solving equations. And again, this was algebraic. I'll write that neater. Algebraic equations. If I ever write something and you can't read it, don't hesitate to ask me to rewrite it or clarify what it is. And so earlier I mentioned that, math isn't the focus of the class. Math just happens to be the language of the universe that explains the relationship between different things, right? So we use equations to say how things are related to each other, right? So you might hear me say stuff like, well, these are linearly related, quadratically related, inversely related throughout the semester, right? And that's talking about a mathematical relationship between two different variables. And usually the variables, they have some physical meaning, like pressure, volume, temperature, and we're looking for the relationships between them. And so generally, when we're doing that, we're either plotting data in a specific way, following an equation, or we need to isolate one of the variables in the equation. So here, this is going to be an equation of just one variable, right? So this would just end up looking like a vertical line if you were to plot something like this. But if we wanted to solve an equation like this for the variable, which was x in this case, what are the steps that we would have to do to isolate this variable? Yep, first thing we'll do is we can subtract 8 from both sides. And so when we do that, we get 2x plus 8 minus 8 equals 14 minus 8. The 8 minus 8 gives us 0, so that goes away on this side of the equation. That leaves us with 2x is equal to 6, right? And so whenever we're doing addition or subtraction, we just have to do the same thing to both sides of the equation. The reason that we can do this is effectively like adding 0 to the equation. And then we have 2x minus 6. What do we do for the next step? How do we isolate x? Yep, divide both sides by 2. I'll put that right here. So we have 2x equals 6 divided by 2 divided by 2. So this is kind of the reason we're allowed to do this is kind of like multiplying 1 to one side. So what happens to 2 on the left-hand side of this equation? They cancel out. That 2 cancels with that because any number divided by itself is equal to what? 1, right? Yeah. So that when we add and subtract, you subtract a number, that goes to 0. But when we're dividing and multiplying a number by itself, that'll go to 1. So we get x is then equal to 3. So that's how we isolate a variable here, right? So that's probably the most, complicated form of math. We probably, once we get to pH of solutions and stuff like that, we'll deal a little bit more with things like logarithms and stuff, and I'll talk about that in a couple slides. But we want to be comfortable just being able to manipulate a simple equation to then solve or for isolate a variable, right? And a lot of times this isn't necessarily going to be all numbers with one variable. A lot of times we'll have an equation that is entirely composed of maybe 5 variables, and you want to just isolate one. So we want to be comfortable using numbers and also variable representation of numbers, right? Okay, so here we have 2 different equations. Well, why don't you guys take a second to solve for m in both of these equations, right? So before we had exclusively numbers in one variable. In both of these, we have no numbers anymore. Everything will just be in terms of variables. that's a little confusing. So this is m delta T times C. Do that. All right, so what did you get for A?
It is Q
Mm-hmm.
divided by triangle TC.
Mm-hmm. Triangle T, C is equal to M, right? So really to isolate M in this case, you just had to divide both sides by, and you can do it all in one step if you're comfortable with that. You divide both sides by delta TC, delta TC. On the right-hand side, what happens to those variables? They all cancel out, right? Write that neater, delta TC. Those cancel out and those cancel out. So all you're left with is M. I did them both in the same step. You can do them sequentially if you want. And also, does anyone know what delta means? Change, right? It means the change in something. So we'll see a lot of that throughout the semester too. Delta T, this means the change. And uppercase T is usually temperature, but it can be any variable. And does anyone know what that change is equal to? Right, if we had to plug in values for delta T, what would you say you're looking at the change between? Generally, when we're looking at change, we're looking at the difference between some final time or temperature, right, and some initial temperature. So we can write out explicitly what delta T is just as TF minus TI. That's not important for this problem, but it's something I just wanted to introduce right now, right? The change in temperature is always the final temperature minus the initial temperature. If it was distance, the change in distance is the final distance minus the initial distance. So that can be any physical quantity when we're looking at the change there. Okay. Any questions on that? All right, and what about for B? This one is only a singular step. How do you isolate M here? Question? You multiply by what? V, right? So multiply by V to both sides times V. What happens to V on the right-hand side? Cancels out. M equals V times D. And this is an equation that we'll look at probably in a couple lectures, equation for density, right? So this is just algebraic manipulation of equations, right? And these equations represent relationships between different things that we might be interested in. The left-hand equation, that's ultimately the heat of a reaction or a physical process and how it's related to the change in temperature. Those are the things we're looking at. Density is if we have a physical property like the density, how is the density related to usually the volume of the substance that we're looking at. All right, any questions?
What does Q stand for?
Q is what we call the heat of, if it's a reaction or a physical process. Q is an energy term, right? So C is gonna have units of energy per mass temperature so that you end up with energy on the left-hand side of the equation. That's more related to thermodynamics. This is a popular equation that people use if you want to find the caloric content of food or something. You put it in a little how do you describe it? A little bomb calorimeter. You blow it up and then you measure how much heat was released. That's how you can measure how many calories are in food. But we'll talk about that a lot more in the future. Okay. So then we also have scientific notation. So a lot of times people are like, well, this seems like a less convenient way to express things. But generally, if you're dealing with very, very large or very small numbers, it's useful. So why might we be dealing with very large or small quantities in chemistry? Specifically in a lab setting. Does anyone have any idea? Atoms are very, very, very small, right? So if we get a liter of something, which is a normal size to us, that's going to have a very, very large number of atoms within that liter, right? So it's useful to kind of have a shorthand notation when we're dealing with very, very small or very large numbers. Very small, the size of an atom. Very large, the number of atoms in your cup of water, for example. And so the general form for scientific notation is something like a times 10 to the power of n. A is defined as the coefficient. Does anyone know what values a should be between? 0, and so it's you're kind of on the right track. You're one order of magnitude up you need to go. It should be between 1 and 10, right? Because those are the order of magnitudes where if it's anything larger than 10, we can change the exponent, or if it's anything less than 1, we can change the exponent, right? So this is the coefficient, and a usually needs to be between 1 and 10, right? So this is in the quality that I wrote. It says that a has to be larger than 1 and a has to be less than 10. And then we have our exponent, n. And what does n tell us? So I can have an idea. The coefficient really holds the specifics of the number, meaning that if you want to look at the actual value, what integers are in the number, that's held in the coefficient usually, because you can have like 1.2223339 or something like that. The exponent tells us something else about the number, right? So we said it's useful to express very large or very small quantities. So what do you think the exponent will tell us?
If it's large or small.
Yeah, that'll tell us the relative magnitude or how big or small the number is, right? So this tells us how large or small the number is. And n can be larger than 0, or it can be smaller than 0. And it's always going to be an integer. So when I say an integer, what does that mean? It's just a whole number, right? This just means a whole number. Right? It would defeat the purpose of making things simpler if you had like 0.5 as an exponent, because why do I have a square root to make things simpler to understand? So it's always going to be a whole number. So there's going to be a whole number that can be either positive or negative. So if n is greater than 0, that means that it's going to be on the larger side of numbers, right? It's a large number. And if n is less than 0, that's going to be a small number. A small number and large number, that's all relative though, right? Nothing is really large or small if we're not comparing it to something, right? Like 1, we can think, well, that sounds like a small number, but 1 compared to 0.0001 is a large number. All right, so that's the basics of scientific notation, or that's the actual notation for scientific notation. It's always going to be of that form. Am I good to go on to the example, doing some calculations with that? So here we have a large number, right? And to write this in scientific notation, really what it boils down to, because we have 10 to the power of n, is that's just moving a decimal place left or right in a number. If we move a decimal place left, that means that n is going to be a positive number. If we move it to the right, then it's going to be a negative number. So how does this work? Well, here is the original decimal place. Right? We want to make sure, we're going to move that decimal place so that it is a number between 1 and 10. Right? So we move this decimal place 1, 2, 3, 4, 5, 6, 7 spots over, right? So we've turned this large number now into one that's between 1 and 10. So now this is going to be our coefficient. right? Our coefficient is where the integers, the non-zero numbers, as long as they're not zeros sandwiched between non-zero numbers, in our large number, that are left over after moving this decimal place. N, does anyone know what n is given by? It's 7, and so yeah, so 7 is the number of spots that we move to the decimal place. All right, so that's going to be 7 because we moved decimal 7 spots to the left. In the left, that implies that n is greater than 0, right? When we move decimal places to the left, that means that n is going to be larger than 0. It's a positive quantity. And kind of the way we can think about this is every time we move a decimal place to the left, it's like pulling out the number 10 or dividing by the number 10, right? Whenever we divide by 10, we move a decimal place over. Right, so if we pulled out 10 7 times to represent this large number, we have to multiply it by 10 to the 7. So that's for a large number. We move it to the left. All right, is that confusing, or does anyone have any questions on that? No? All right. Okay, what about for a small number? Well, now we're going to do the same thing. We're going to move the decimal place until we moved it to a spot that the integers that are left over are between 1 and 10. What's left over is going to be our coefficient. And then the number of spots that we move the decimal is going to be our exponent. So this now is going to be our coefficient, 6.42 times 10, and we moved the decimal place over how many spots? 3. So now that's going to be 3, except this is a small number, right? So that means that it should be like dividing by 10. Every time we move the decimal spot to the right, it's like multiplying it by 10, which means that this has to be a negative. All right, so 3 spots means n equals 3, and then moving to the right means n is going to be less than 0. Right, because to get 0.00642 to look like 6.42, you have to multiply it by 10 each time you move the decimal over. So to counteract the multiplying it by 10 to the 3, you can divide it by 10 to the 3. Right, because just as an aside, 10 to the minus 3 is like writing what? How else could we write that? Does anyone remember? If we have a negative exponent, what is that? It is. So it is a form of decay, right? And so another way that we could write that is it would be like 1 over 10 to the 3, right? So 10 to the minus 3 is like writing 1 divided by 10 to the positive 3, right? So whenever you see a negative exponent, that's like the same thing as writing 1 over the same number to a positive exponent, right? Because if, let's say it wasn't a number, it was a variable, that means that it would be getting smaller if it's negative. And so that's why I said for multiplying, it's like dividing by 10, moving to the right is like multiplying by 10. And so it's basically like we have to account for this by dividing by 10 to the 3. Really, because really the only thing we're doing here is we're just writing this number in another form, right? So it's less math and it's more kind of like language, right? How do these two things relate to each other in a different language? Okay. All right, so we'll stop there.